Okay, here's another short video expounding on what we've learned last week and also what we learned in the classroom this week. Um, we did drive-by centimeters last week, and we saw great success already. By Friday, RoboKite Yellow had completed some missions, and we're on their way to completing more. So the power of being able to drive distances reliably on the board has definitely manifested itself, and everybody's been taking advantage of it. So now it's kind of time to take it to the next step. RoboKite Black already started doing that, but raised some interesting questions, and I'm going to kind of explain what we saw all together and how we can possibly solve those problems. So I'm going to start with our code from last week, obviously in Scratch. So before I do that, I just want to show everybody something real quick. So here was my project from last week. You can actually, if you want to make copies of things, because of the no ability to import export really, probably the best thing to do sometimes is actually just make a copy of your project. You can make new ones, of course, but since I want to start with the code we had last week and then make it a little bit more advanced, I'm going to do this, and we're going to say drive centimeters loop, and I'll explain later why we're doing this. So the main thing RoboKite Black came up with was they were trying to combine driving distances with other things. And it's something I very rarely see on the internet, even in tutorials. You'll have how to drive distances. Then you also have how to drive with proportional control, whether it's gyroscopes or line followers or other things like that. But inside the line followers and other things, they're usually just maybe forever loops, or they just drive for a certain period of time. So what I'm about to show you is the challenge that's presented in order to combine both of them together. The competition team last year had great success in combining this, so I think it's a very important concept to learn. And once it makes sense, their code became mature enough that they could accomplish things repeatedly very, very, very quickly. So we're going to go ahead and open this up here in Scratch now that I've made a copy of it. Okay. Okay. So same code as we had last week. Looks straightforward, works well. So here would be the temptation. So let's pretend that every time I jump through this area right here, that I want to do something with my robot to correct it to go straight. And that's what your, let's just say sensor controlled, doesn't matter if it's PI or D, but let's just say sensor controlled movements to get things back straight again are doing. Now, the temptation always is to do something like this. And this is what everybody was doing. I threw these blocks off to the side before just to save some time. Is to take a reading off your sensor and then use that to make it go left or right. So this is the block that turns our robot. We've all seen it. We've all used it. And what this basically would be doing is checking for an error on the gyroscope and making it come back to our line, same as colors or anything else like that. The problem with this is that, and as some of the teams have already seen, is that it just goes through this loop one time. So it's going to make one correction. That's not good enough if it's driving any distance. I will tell you that the folks at MIT said a regular loop can process at almost 900,000 times per second. That's not going to be the reality on a robot, and the more blocks you have in there, it's going to get slower. But let's just pretend it's a couple hundred times per second. So what we want to happen is this to be corrected over and over and over and over again rapidly. So we need to come up with a different method. And the best method is to make your robot just drive and keep correcting it over and over and over and over. That means we need to introduce a loop. Distances with loops present a different problem because we needed to stop at some point in time. And that's why I think sometimes on the internet, you never see that happen. So I'm just going to start with distances and loops period here in general, because that's going to be the foundation to everything else we need to do. So I'm going to put our code back the way it was. In fact, I'm just going to trash these for the moment because we don't need them anymore. And figure out how to make this code drive with a loop. Now the challenge becomes, how are our sensors going to break out of the loop? So we know we could probably put a loop out there. So we're definitely going to start with that. So we're going to do a repeat until loop over here. And what we're going to do is put in a moving block, same as what we have here, but we're just going to change some stuff. So I'm just going to toss this down here for the moment. So a moving block now is going to be just moving straight at some speed. So let's see, set movement straight, period. So start moving at a speed. So this is just going to keep looping until it's done. Now, what we want to do, we can go ahead and just pull power in here because obviously it's part of our equation. But what we want to do is have this block keep running until a condition is met true. I wish that they had degrees counted for rotations versus honestly degrees. They don't. So we're going to have to play around here a little bit. So what we figured out last week is that one full rotation is this centimeter value down here. So now, unfortunately, we need to kind of convert that into degrees because that's the only block that I have a choice with right here. So I've already done that here, so you can kind of see what it is. So we're going to grab this value, but all I did is take 360 degrees, which is one rotation, and divide it by the total amount of centimeters that could exist out there. So that gives me how many degrees is 1 centimeter. So when that motor rolls 1 centimeter, it's going to be 20.4 blah, 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 blah degrees. So this is going to put me in a spot for us to kind of babysit the motors. So in order to do that, we're going to need some type of a and or greater than, less than value or something like that. So everybody's temptation is to do this. So I'm just going to do it for a minute and explain what probably would happen. So had I done this, okay, and then set it equal to what we want it to be. So distance in centimeters. Well, we're going to need another operand in here. So need some math here to figure out our total distance. So this is what we just calculated a minute ago, very similar to down here. So it's going to be however many centimeters we had to equal the degree, and times that big old giant number that we just came up with. Okay, so this is what everybody's tempted to do all the time. The problem is, if I can connect here, the problem is that these degrees do not have decimal points. This is very, very, very specific. This will never become true. You'll have to take my word for it. You're welcome to try it on your own, but it's never going to become true. And it's because of the decimal points in there. So when these motor rotations happen up here, it's going to have a decimal point in it, and it ain't going to happen. Okay, so how do we solve that? Well, the easiest thing to do is take a little different operator here and do greater than. So now you're talking about fractions and fractions on the time. I mean, it's going to be so fast that you should never notice it. So we're going to say the exact same formula as up here. So when degrees counted equals, I'm going to grab this whole inside block, is greater than this, then stop. We just can't use equals. It's tempting because you want to say, oh, whenever it equals that, stop, but it needs to be greater than. So now we have something here. if we did this, it should drive the distance in centimeters that we need based on it counting one of the motors. Now, another thing that we can talk about here just real quick, it doesn't matter which motor you count. We're going to make some basic assumptions that the robot is driving straight. And if the robot is driving straight, both motors should be rotating the same amount of time. Now, I would probably take a reset motor block and stick it in here. It's not going to matter when I run this test right now, because anytime I start up my program, it's going to reset the encoder. That's what they're called. That counts your degree rotations. And when it does that, it's going to go back to 0. So this code should already work at this moment in time. And if we feed the same thing in as we did before last week, we should be in good shape. So let's go ahead and give it a whirl. And pull this up here. This is a 10 centimeter strip again. Same power, same everything. Let's see what happens. Okay, so it did it. Everything worked okay. We're in good shape. Now here's a couple of caveats here, and this is where the code will start to get more and more complex. Last week we drove backward. That's not possible with this code right now. Now, is it important? Ultimately, yes, it is. It will be important at the end of the day. We will have to get back off the board, and sometimes you don't want to turn your robot around before you do that. We can already start thinking of strategies and what to do. I think the next thing to do is to figure out how to get the KP in there for the sensor stuff, or making your robot try to go straight also. Again, even with the basic code we had last week, teams had a bunch of success in scoring points, and they were able to do it repeatedly. So you're well on your way to being in really good shape with some of this basic code. Inverting stuff here is, if you think about it, what's going to happen is this will never become true. So if I made my centimeters negative and everything's driving backward, these values are going to become negative too. So this will never become greater. If I try to do it, in fact, I'll do it for fun just because the robot's here. So I'm going to tell it to go minus 10, just like we did last week. I'm going to pull the camera back out here, and you'll see that this robot ain't going to stop until I tell it to. In fact, it didn't do anything there, but I'll try it again. Because it came greater than a negative number. Sorry. I'll just do this. This will be the same thing. Bye-bye, Mr. Robot. Okay. So, and if you look up here, all these degree motor calculations are minus 2,000 and stuff. So this never became true. It didn't like it because in the first place, when we fed distance in there as negative, it probably knew it wasn't possible for it to ever be greater than a negative number. So maybe that's why it just didn't run, or it didn't compile at that point in time. But same principle. So now we got a problem when we drive backwards, so we need to think about it. But this puts us in great shape right now in order to put our code in there that corrects our robot hundreds of times per second. So that's it for this session. We'll figure out next time how to put in the KP values and the proportional corrections, at least for the gyroscope. And then from there, we'll start talking about some other things like resetting the XY rack on your robot. You will see when you start to try to do missions that you will need it set in a consistent spot over and over. Thank you.